Okay, page 3 of the memory allocation notes. So in one of the annotations on the previous page, I mentioned that there's this hidden bin. So the hidden first bin is a bit vector that represents non-empty bins. So if you remember back to the fixed priority preemptive scheduling, the data structure I drew on the previous page looks awfully similar to that. And it's not used in exactly the same way, the bit vector, but it allows, when malloc is looking for a bin of the right size to satisfy a call, if it's having to do the best fit, it allows one to find one relatively quickly. So let's look at these chunks that I've been talking about. And this is not an exact representation, but it is how Doug Lee describes it on his webpage, and it's a little bit simpler. So there's basically two flavors of chunk. So we have allocated chunks, and they're pretty simple. What you have is a double word at the start, which tells the size of the rest of the chunk, and the rest of the chunk is the data. But there is also some status information, and in this case the chunk is in use. And this pointer here, or this address here, is called mem, and this is what is returned by malloc to the program. So this is the address returned by malloc. You don't want the program overwriting that size data, because that will be important when the chunk is returned by free. And then we have the free chunk, free chunks. So there's still the size information, and then in this case the status is free, so that's all stored in a double word. So on our ARM processor, that would be an 8-byte row there. And then we have a forward pointer and a back pointer, and this is used to build the linked lists in the bins. And then whatever is in the middle of the block is unused, and then finally it finishes again with the size. And so I said that this wasn't exactly how it's implemented. This is how Doug Lee represents it on his webpage. So I'll use the goldenrod here. So what actually happens is that the size of the previous chunk is stored as part of the current chunk. So this, you don't even have to draw this in, because it'll just confuse you later. But this part here is stored at the front of the chunk. So if you look at the glib code, it shows you a diagram in the comments of what a chunk looks like, and so the previous size chunk is stored there. Anyway, just an implementation detail. So here's an example of a bin. So we have a free chunk here, and then I'm going to spread them out a bit. So we'll have, and these can be all different sizes. So free, free, and in between them you can have allocated chunks. So I'll do those different color. And so on. So each of these is a chunk. And if you look at the structure that I showed you for the free chunk, it has size information at the start, and then it's got 2 pointers. There's a back pointer, so let's say that this free node here is the first in the bin. So its back pointer would be null, and its forward pointer would point to the next free one in the bin, and it doesn't necessarily have to be in the order that it shows up in memory. So let's point it over at this free one here, and this free one here, its forward pointer would point to this chunk here, and this chunk, if it's the end of the bin, then its forward whoops, I got that wrong. Its forward pointer would be null, and then we just need to add some back pointers here. So the back pointer from this chunk would point to here, and the back pointer from this chunk would point to that one. So looks like a mess now, but hopefully you get the idea. It's a linked list. So one more point. When a chunk is freed, it is coalesced, meaning to be combined with surrounding, and I'm going to say, just to emphasize this is contiguous free chunk. So let's just say that the first allocated chunk in this diagram here gets freed, then that would be coalesced with the 2 free chunks to either side of it to create one big free chunk. And the purpose for doing this is to it reduces fragmentation. And I've shown you a fairly simplified view of how Malloc works, but that's the main concepts are there, and the rest is really just optimizations and other bells and whistles and so on.